Um, a little bit about me before we get started and the title of this presentation. I'm Bram. I am a OpenAI developer ambassador, but I'm also just kind of like a Zettelkasten PKM second brain enthusiast. I've been using my tool of choice, which is was Obsidian, for a number of years, and kind of like built some stuff for that community as well. And these days, I actually work on my own software for Second Brains called Your Common Base, which we'll be talking about later in the presentation. But largely, what this presentation is going to be about is actually the theory of kind of like cost and cost mitigation for kind of building these second brains and scaling them to a size where they're either at the organizational scale with a number of people, but also just kind of like the scale of a human's lifetime, where you're capturing a lot of different information from a lot of different places, be it photos or text pieces or quotes from books. And we're going to talk about how to keep the costs of that system low. And I don't necessarily mean real monetary costs, but there is some overlap there. So let's get into it. So this is going to be the outline of the talk. It's going to be relatively technical, but it's really only for the purposes of proving out the cost information of these models in the real world, and kind of like the trade-offs of what might happen in practice and theory versus what actually happens when you implement these tools in on Earth. So what we'll be talking about is the problem of search, brains and computers. We'll talk about brains and computers first, and particularly the kind of like distinctions and differences between how brains and computers store and process information. And then we'll talk about the problem of search and add, and how those two things are kind of inverse to one another. Then we'll talk about strategies and techniques versus data structures, and kind of like discover what the difference is between a strategy is and what the difference is between like a data structure, which is a computer science term that I'll also be defining when we get to it. Next, we'll be talking about the tyranny of tags and headings, and obviously that's a pretty bombastic kind of term, tyranny, but once we get there, you'll kind of understand why kind of tags have held such a strong hold on kind of how we kind of organize information, but maybe how there's other strategies that we can try that are a lot more effective. And then finally, we're going to talk about potentially using a way forward, and that's going to involve all of the kind of conversation that we had about the rest of this talk up until that point. So let's get into it. So let's start off with the problems, and kind of enunciate and elaborate the types of problems that we're working with. So first problem is the problem, let's start closest to home, is the problem of our brain. So the brain is an information processing machine. Whether you're taking in information about how much light is in a room, these are very simple things. How many apples you can count in front of you, how many kind of like the feeling of the temperature on your skin or the rain on your skin. This is all information that's being fed into your brain, and it's deciding what to do with it. If you're raining and you're not wearing a coat, it says, oh, well, maybe we should get a coat or a jacket because we don't want to catch a cold. And that's because it's dealing with the information of the rain happening in front of it. So there's a lot of things that a brain can do, and we'll talk a little bit about this as we get a little bit further into the presentation. But some of these categories include storing, which is like new memories, searching, which is kind of like, what's that person's name? They're walking up to me, I'm trying to remember. Recontextualizing, which is kind of the idea of taking something and turning it into something else. And that's literally sometimes a direct replacement, which you can see sometimes through cognitive biases, for example, or just kind of like, seeing the bright side in something, for lack of a better term. Judgment, which is kind of like the ability to look at a piece of information and decide if it's a threat or an opportunity. And then creation, which is the ability to synthesize information, new information, from old information that was already had. So what the brain isn't is a computer. It's not a steam engine. It's not a hydraulic pump. It's not a watch. It's not all these other technologies that people like to analogize the brain to. The brain isn't any of those things. And there's actually, you can see here in this footnote, if you scroll to the end of the talk, that there's a quote in the extended mind where there's just like this, there's this kind of drive to take the latest technology of the era and assign brain functions to it, because it just feels like we're trying to describe more about what the human brain is. But none are really fully adequate or accurate, because again, the brain it's a different thing, and it doesn't necessarily need to be these things to still be impressive. What the brain actually is it's a biological organ, whether it's in a squirrel or a human, that is embodied in an environment that forces it to evolve by dealing with new information constantly. Whether that new information is just the changing of the seasons, or that new information is kind of like your stock portfolio just dropped, or that new information is a diagnosis from your doctor, or that new information is just anything, right? Your brain has to deal with these situations, and it has to come up with judgment calls to be able to deal with these situations. My mouse just disappeared. Okay. The brain, however, and I think that this is kind of important, interestingly, is not incentivized to store or recreate information perfectly. And there's a number of reasons for this, but again, mainly it has to do with the fact that the brain is embodied and that it lives in an environment. So the brain actually has no incentive to tell the truth or store things as they accurately were, because it only really needs to do it for its own purposes in the environment that it's in. So if it needs to cognitively distort something in order for that information to become tolerable, like forgetting a traumatic event, for example, it will go ahead and do that, because that's exactly what the brain has decided to do. It's helping the survival of the overall organism, and that's its task. And then we get to computers. So the computer is also an information processing machine. I just said the brain isn't a computer, but they both do process information, but they do it very differently. So here's actually an inclusive list of what computers can do as of 2024 when I'm giving this presentation, and this could be different in the future, so that's why I put 2024 in there. Computers can write information and they can read information. That's all computers can do. That's it. Everything that we've built onto computers as software are abstractions on top of these two functions. So anything that you see, whether it's this Google Slides doc presentation, or loading Instagram onto your phone and watching a video, or having a real-time conversation with someone thousands of miles away, it's just happening so fast that it gives the illusion of other forms of processing. It's literally just reading a memory thing and then writing another memory thing really, 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 really quickly, like billions of operations per second. So for that reason, computers are traditionally really, really good at crunching numbers. So they're really good at staying on target and staying completely focused, but they're very bad at understanding relationships or cost reward, because they don't have to actually deal with threats or opportunities. They just map everything to zeros and ones. So that means that computers are incentivized to store and recreate information perfectly, because if they can't recreate it perfectly, the data is corrupted and your whole system shuts down, right? You've seen the blue screen of death on Windows and things like that too. This is all just computers basically failing to replicate the information to the acuity that it was stored in. So now we talked a little bit about how brains and computers are different because they have different incentive structures, but they also process information differently and have a different understanding of information. Whereas, like, again, in a brain, particularly when it comes to understanding a particular topic, the concept itself is embedded in the neural architecture because the neurons are alive too. So now let's talk a little bit about searching and adding. So searching and adding, as it comes to the set of our kind of like our data. So you have a list of notes, whether that's journal pages or documents at work, or kind of emails to get through, whatever. There's an irony of kind of how data is stored in both computers and brains, that the easier it is to add something to a set, the harder it is to find that thing later. So like if you, for example, the opposite is also true, for example. So if you have much more upfront investment in adding something to a list, the difficulty of finding it later goes down quite significantly. So an example of this that's really easy to understand is maybe like a clothes pile versus a closet. So if you are taking a new pair of pants and you want to just throw it onto the clothes pile in the middle of your floor, that costs you like 0 seconds to do, right? Because you just throw it on top of the pile. And if you only have 3 pairs of pants, it's not that big of a deal. But if you have 30 pairs of pants and you're looking for a particular pair of pants and you have this giant clothes pile, every single time that you want to find that particular pair of pants, you have to go through 30 pants. But if you take the effort to put things in your closet and fold them and organize them by color or maybe by shape or like kind of like size or the day of the week that you wear them or whatever arbitrary thing you decide, that takes upfront effort. So you have to basically decide, okay, where does this live? But then later on, when I'm searching for it, I can just find it basically immediately, because then I can be like, okay, it's in the Thursday pile, or it's in the blue jeans versus the chinos or something like that, pants. So you can see this mathematically in the algorithms themselves. search goes through a list to find one thing. And there's a thing in computer science. I studied computer science, if it wasn't clear from the way that this presentation is trending, where we call it like big O, which is basically this, what is the amount of operations that it takes to do a thing. So when I say big O of n, I mean to say that like you have to look through the whole list to get something from the list every single time. Where if I said O n squared, that means that you'd have to look through the list, not 2 times, but the square times of the looking through the list. So you look through every item twice. So add appends every time you search, which means that as you add, you are literally increasing the cost of search. And we can see this as an image kind of played out here. So like what I have here is 2 images of kind of like this upfront cost of addition, like I was talking about, and then how that affects searches as your number of records goes up, the cost. So like you can see here that when you have a low amount of records, or excuse me, a low addition cost, the cost of search just keeps going up and up and up and up and up and up, and just kind of like continues forever. If you impose a really strict rule to start, you can kind of ameliorate. Sometimes this line will still go above this line. The search will go above the add, but often you can try and get it to level out at the very most, right? So it's like it'll never be 0 to search, because again, you are imposing some kind of cost to look for items, but you can hopefully keep it lower than the cost of adding. But the problem is now every time you add something, you have to impose this cost, which also in its own right becomes its own stressful point, right? So ideally what we want to do is we want to get computers to do this thing for us, right? We want to take our adding as humans and keep it at this low cost in theory. But then what's happening behind the scenes is that a computer is taking on the cost of doing all the high addition stuff. And then what we see is like a better search result, but we also don't have to impose that cost onto ourselves. So a good example of this is PageRank for the way that Google does things, right? They basically imposed a list of rules that says like SEO, look for titles that match this is what if they're in a 5-mile radius of X, Y, and Z. And that's also like filters, for example. So you can say, hey, filter for something that's, only green, only return the green results, or only return image results, or only return video results. FullTech Search is something similar, and we'll talk about this in a second with this, which is the Dole example. So if I search Dole on Google, right, you imagine that I should get Dole, the banana company. But what if I was looking for Bob Dole, right? So like the concept of the FullTech Search and filters and stuff like that are only really useful until you provide the right amount of context. So if I say Dole fruit, I mean the thing on the left. If I say Dole politician, I mean the person on the right. And the being able to distinguish between those two is where a lot of the nuance of search and ad come in. So a thought here could be like, okay, so does that mean that we can just be more strategic, right? Like we can keep adding all of these strategies like FullTech Search and PageRank and stuff like that. We'll be fine. We can just keep doing that forever, and we'll never really run out of. We'll keep those search cost lows, and we can kind of like move forward with that. The problem with that is that strategies have their own kind of issues, right? So what is a strategy in the first place? So a strategy and a technique basically give our system boundaries. These are the boundaries that I was just describing, mainly being kind of things that apply rules for things that get added to our system and things that get searched from our system. Strategies and techniques are also known as kind of like algorithms because they accept information as input and then they transform it to a particular type of output based on a number of rules. So like para is a good example of this, or progressive summarization, or Zettelkasten, which is basically this idea of saying like, oh, if this is undone, then put it here. Or if this is a atomic entry, then use it in a Zettelkasten. Or if it doesn't look done, then use progressive summarization. And I'm not trying to say that these strategies aren't useful and they aren't impactful, but they do have pretty significant downsides. One main one being that they all require a buy-in or a learning curve in order to utilize the system as it's made. And the responsibility falls on the operator, whether that's human or computer, to be able to maintain those system rules over time and then teach them to the next generation too, for example, right? So there's this basically extra cost that's imposed every time that you want to add a new strategy to your system. And some strategies are better than others because A, they're easier to teach, but they're also easier to maintain over time. But data structures, on the other hand, are immutable features of sets of information. So a data structure is literally the set of information itself. It's the list of all the files and the folders and the stuff on your computer. It's the static storage, the space itself on which the information is stored. And it's where you can, these are the containers from which you can run these strategies and techniques on your hardware. If there's anyone watching this who is a computer science person, you might know functional languages, for example. And functional languages are taking data and then running functions on top of them. That's kind of what data structures are useful for here. So what we want to do is that we actually want to use algorithms as strategies on operations on top of smart data structures to manipulate our data. We want to use data structures as our low-level rules of engagement and then build strategies on top of those. So data structures might be trees, lists, dictionaries, and stuff like that, which all have their own trade-offs as well, actually. So now let's talk a little bit about how this applies to knowledge management, specifically through kind of something that we're all familiar with, having done knowledge management for a while, which is tags and headings. So in order to filter a large set of information reliably, we all pretty much end up in the same place. We all are just like, okay, I'm going to tag this as this, or I'm going to store this under a folder that looks like this, or a box that looks like this. And those are both kind of tags and headings. Tags are basically a bottom-up taxonomy. So multiple tags can be applied to one piece of information. And headings are a top-down taxonomy. They're like folders, they're boxes, they're kind of like this belongs in this, everything belongs in this room is in the folder of the living room, right? But necessarily a couch doesn't necessarily need to be in a living room. It can be in other rooms too, right? So tags and headings are actually closer to data structures than they are strategies, which is why they've stuck around so long, and which is why they appear in so many different types of strategies and softwares. So people will kind of like take tags and they'll use them in Obsidian. They'll also use them in Notion. They'll use them in Evernote. And the reason is because they interface with the data directly. They don't interface with the strategy that's interfacing on top of it. So this is a visual example of kind of like what a tag looks like. So you take a note and you apply multiple tags to it, and then every single time that you reference this tag, it points to that same note. So this is the note that it's being referenced to. Whereas like a heading, you actually have to duplicate the data. So if I have two headings and I want this in both places, I need to copy this and then move it over here too. So there's trade-offs to why you want to do both of these things. Headings tend to be better if you want to like group things together, but you kind of like know that they all are kind of like structurally forming a bigger argument. And tags are better if you want to have something appear in multiple different places. So what are the problems with tags and headings? The problems is that conceptually they're really brittle, right? So in order to use them, we have to load into our minds an entire second system of the tags and the headings that we chose to use. One that recalls all of the tags that we set up or the structure of the headings that we set up. So basically a table of contents can become just as long as the actual data that you're attempting to store. So if it takes you an hour to search your table of contents, what's the point? Basically, right? So it's like, how many tags is a good example, right? Do you have that are basically just the same thing or spelled slightly differently from one another? You might have snow and kind of winter, but they both are kind of the same thing, right? How many times do you struggle to decide what heading something belongs to, or a folder, or if the heading is no longer accurate? Like what happens if it's stale, for example, right? So this happens all the time where you have a new piece of information and you're going to figure out where to put it, and you have some headings and you're like, does it go in this folder or this folder? Like, I don't really know. Maybe I need to make a new folder. So what do? Vector embeddings is going to be the first thing that we talk about that might be able to get us out of this predicament. So vector embeddings are a way to use machine learning models to convert natural language into numerical addresses. And this is kind of a little bit technical, but there's going to be some pictures in a second. This allows computers to use an algorithm called cosine similarity, which is kind of outside of the scope of this conversation, but to search through massive data sets extremely quickly, doing what computers are good at, which is really reading and writing very fast. Excuse me. So these addresses are actually created by machine learning models by assigning distances between concepts, effectively turning concepts into a data structure. This isn't exactly correct, but this is in the fact that you do operations on top of this new data set that you couldn't do on the initial data set and make it a new data structure. So the reason and the way that these things work is by merging societal concepts of objects into a format that can be leveraged by individuals. And this is a very powerful technique that allows us to take the societal's concept of Monday and put it close to Sunday, but also put it close to the most annoying day of the week, right? These are concepts of like being able to figure out and kind of suss out through a ton of data on books and the internet and everything like that, is like, what is the relationship between this and this? And interestingly, to go back to the brain for just a second, we notice that in young children, for example, they'll always ask why, why. And one of the reasons that they're asking why is they're trying to figure out the relationships between things. They're trying to test the boundaries of where things actually end and kind of figure out, okay, so this is related to this, but only in this circumstance. Or in this context, I should sit like this, but in this context, I shouldn't be like this. I can wear these clothes in this context and not in this context. So basically, we take these societal concepts and we merge them into numbers for computers. So here's an example of what semantic space actually looks like. So you can see, for example, things like nuclear power, nuclear bomb, apocalypse are all really densely clustered together, but celebration is further away, even though it's closer to joy, it's closer to drunk and alcohol, right? So you can kind of start to see how you can almost flow through these concepts into another. So you go from celebration to joy to alcohol to tobacco, and then you get to lung cancer and you get to death and you get to apocalypse and nuclear power, right? So you kind of like start just like, right? Like you move through concepts and you jump from concept to concept. And what's really interesting is that this works in people too. There's a game called the association game or something. My friend actually taught me once many years ago, where basically it's a game you can play with your friends where you start out with a word and then you say like, I'm going to count for 10 seconds and I want you to basically jump through words and then tell me what word you ended on. And then I have to try and figure out your path of how you got there. So like, for example, toaster, men, right? If after 10 seconds you said men, you're like, oh, wow, I don't even know how you got from toaster to men. Like, it turns out that this person followed the path: burnt, split, lightning, grease, slick, sick, nausea, ocean, glass, green, teeth, tongue, fork, road, fall, cello, bass, river, men. You know what I mean? Almost completely random nonsense, it feels like. But for someone who's a little bit more kind of like focused, toaster is related to bread, butter, jelly, peanut butter, grapes, strawberry, fruit, salad, cucumber, cheese, lettuce, carrots, raisin, banana, cereal, Fruit Loops, cinnamon, sugar, cinnamon toast crunch, sugar, cake, right? So you can almost see that, like, for somebody who has maybe a little bit more of an out there, quote unquote, brain, they kind of just jump to toaster and end up in river and men and bass. And then that's kind of like how they have these really creative associations. But if you still stay toaster and cake, you're kind of still in the same neighborhood. You're in the same cluster. So like you can actually see this kind of visualized here too, where they've done like these free association from the members who were tested to be more and less creative. So the people who are more creative aren't afraid to kind of like jump really far in their clusters. They kind of like make these really far leaps, whereas people who are less creative and a little bit more kind of like mathematical or a little bit more computer oriented, you might call them, tend to stick within a cluster and they don't want to kind of like jump out to random ideas. So, you know, as this relates to a solution and kind of like where this talk is heading is kind of like, okay, so we now know that, you know, things can be stored using computers. What does that actually mean for us? Like what benefit do we get from that we don't get already from like tags and headings? And I think that a great place to start is kind of actually just communication with ourselves and other human beings. So generally speaking, and I mean generally as in literally every single time, the information when we want to convey and store isn't held under a tag, it's embedded in the concept itself. And the way that we do that is through basically social contracting. So social contracting is an implicit understanding of like, I know that you know that I know this. So I know that you know that I know that Obama was president. I don't know that you don't know that I don't know that the Plantagenets were a royal family in England in the 12th century, because that one's a little bit more farther out. I don't know that you don't know that I don't know that, like, you know, Scala is a derivative programming language of Java, right? So you know things that I don't know, and I know things that you don't know. But we have contracts of concepts that we understand, and we can use analogies to teach each other these things. And that's how we kind of embed it in the concept itself. And then we kind of reference it when it's appropriate. So this talk is a good example, because as I wrote it, my brain transformed some, not all, of the thoughts that happen every single day in my head into an artifact. Then your brain, who's watching this right now, is consuming this artifact and contextualizing it based on your own background and your own understandings, deciding what's useful and what's useless. So from this claim, we can claim that all written information is conjectural, right? So it's all driven from this point of like this person trying to convey a particular thought and maybe succeeding or failing. And then information that's captured on paper or disc or tape is conjecture that was frozen in time for later consumption. So it's turned, you know, the argument as the concept is turned into, you know, wherefore art thou, to be or not to be, is written down, and then somebody 100 years later, 500 years later can read that and kind of try and understand it from their own environment and their own perspective. So you can't store, for example, that experience of a summer night that you have with your friends, but you can imprint it by describing it through words and pictures and other and audio kind of artifacts that we've kind of created, technologies we've created to capture parts of that experience, the sunset or whatever. But you can't relive it. There's no way to actually kind of resurrect it from the information itself. So this brings me to kind of like where I think that we are currently at with information and data structures, and how to move away from tags and headings in a way that treats computers and brains better for these large information sets and keeps our costs low. It's like, can we achieve all of that? Like, that's a lot to ask. And I think that we can. And I think that the way that we do it largely on the internet is through commenting systems, right? So basically someone will post something on LinkedIn or Twitter or Instagram, and it's just a piece of information, and then everybody weighs in with a comment. And when they weigh in with a comment, they're basically improving that information by saying, here's what I think about the thing that you just posted. So what's interesting about vector embeddings and the data that I showed you about like the nuclear bomb apocalypse, tobacco party joy thing, right, was that like they can't really read minds. If you wanted to say that like tobacco should actually be related to partying and that was further away, then you actually have to make a reference to that. You have to say like, okay, yeah, I smoke cigarettes at parties or something like that. You need to literally make a pointer because vector embeddings can't read minds. So this is where the entry and comment model comes in. So you might have a vector for like partying with my friends in Paris, and then you might have a comment that says, this was in 2019, I had a lot going on that year. So now every time that you comment, you search for 2019, it's going to pull up that party, right? So we iterate through all the ways that we know about something, and then we store it as pointers back to our entry. And I have a visual for this in a second. But basically the way that this works is that there's only finite ways to recall a thing before you're just talking about another thing. So like if you start talking about like, so it's like that game of guessing charades, right? Where you're like, okay, I'm thinking of an animal. It's got 4 legs. And you're like, oh, horse, tiger, cow, bear. Like there's a lot of animals that have 4 legs. And you're like, okay, no, it's like an animal that like swims in the ocean. And they're like, I guess like otter. And they're like, no, it's got a beak. And you're like, platypus. And you're like, yeah, platypus. But you could only be talking about a platypus. You can't be talking about all those other animals, even though you shared other things with them. Because again, when you start saying something else, it also has wings. It's no longer a platypus. You're talking about something else. So these pointers change over time. Like I said, the brain is an embodied organ, which means that over time it changes in new environments with new data. So we shouldn't expect our data to just get stale every time that we have the same heading for something, which is why we have to do all that effort of updating our headings and tags in the first place. But we shouldn't have to be responsible for that, is basically what I'm saying. So by using comments to update our way of thinking about a thing, by leaving a new comment a year after on an entry that's a year old, we basically update our thinking to match the new reality that the information find itself in and when it initially got started. So the way to think about this is kind of like, this is the entry that we're looking for. This is like the goal. These are kind of like things that are similar to it through vector embeddings. This is the search that you typed in. So if you just typed in this search and then you ran a vector embedding or just a FullTech search, you wouldn't get back to it, right? There's like, it's way too far away. But if you have this comment and this comment has a pointer to the entry, you can get to it by just searching for the comment. So this allows you to basically travel fairly far distances in your search set while keeping cost of adding really low too, because all you're doing is adding a new comment. So here's the thing about like strategies. Again, like I kind of riffed a little bit about earlier about how I think strategies are kind of like overplayed. And I don't think, obviously that's not fully true. There is a lot of utility to strategies, especially when they're in this kind of entry comment model. So I think that we can and should maintain our current strategies. I think the reason that we came up with these strategies in the first place is because they work, and they do work in a lot of situations. And when they don't work, we should update them, right? And we find new ways to kind of like make these strategies better for different types of data. Like, things that make sense on Twitter don't necessarily make sense for capturing information for books. Strategies, when divorced from the contract of the data layer, give us powerful modes of communication and expression. And this is the contract that I was talking about a little bit with the language itself and the concepts, but also data as in the data structures. So our second brains can scale reliably, and we can try new powerful strategies if we always try to keep the cost of search and ad low, because the second that these costs start to spiral out of control, strategies start revealing their problems, and we start over again. We always break the system. We're like, okay, we're moving on. This doesn't work. And this happens over and over. And that's fine if you're trying to evolve systems and change. But if you want to have like a consistent data set that just stays over time, and then you just apply a new strategy to it, that means that you can take this set of data that you've been working on your entire life, and you don't have to throw it away. You don't have to throw out the baby with the bathwater, for lack of a better term, because this was the strategy that you used to store it, right? So instead, by setting better lower level rules for information retrieval at the data structure layer, we can create more creative modes of strategy to cut through the noise, to find these diverse pieces of information. And this is kind of where the entry comment model comes in, leveraging vector embeddings and things like that. And what this allows for is a collaboration of the way that computers store information, which are basically rocks that can think, right? So they just take raw information of zeros and ones and they move really, really quickly through it using electricity. And humans, which have idiosyncratic, separatable meaning from the things themselves. So it's like when you reference mom or some word that has a lot of emotional resonance with you, it's really hard to just think about the concept of a mother without thinking about your own mother. It's like it's almost impossible because like those two things are connected because that's how you learn them in the first place. So humans have idiosyncratic meaning attached to abstract concepts, whereas computers don't. But we need some way to kind of use both if we want to scale our information, especially in our modern era where we're constantly just dealing with a bunch of information and we're overwhelmed by it and we're trying to figure out what it all means to us and if it's useful or useless. So this is going to be some examples actually from the way that this talk was actually built using this technology that I was talking about. So you can see here, for example, that the way that this works is that I type in something about like, this is what I wanted to do for the strategies and technique slide. And then I run a search that basically pulls up references to entries in the past or comments that point to the entries themselves that reference that thing. So you can see that this one was stored on June 26th and this one was stored on September 1st. And the reason that I really love these timestamps, for example, is that they really kind of like show to me that like information, when you learn it, doesn't mean that it can't be used outside of the context that it found itself in. So it's kind of like if you learn, for example, that like this is a antidote for a particular type of snake, and you live in like Chicago, you're like, that's not really helpful to me. Like that's just useless information. It's just going to take up space in my brain. But if you get bit by that snake when you're on a traveling trip or something like that, you're like, damn, wait, what was that antidote? Again, this is actually relevant now. This is relevant knowledge. So you don't know when your knowledge is going to become relevant. That's not necessarily an excuse to save everything that you come across, but it is an excuse to say like, hey, I think this is interesting and I'm curious to see if it will live future lives, and kind of let the system decide if those things actually come back up is something that's really exciting. So, by running these searches, I basically turn this into a list of numbers that finds the closest list of numbers and then returns those. And you can see here that basically what I do next is the progressive summarization technique, where I underline the things that I was talking about. And this is the information that I use to make this talk. Like this is what I was talking about, folders and files and the data structures. And here I was talking about progressive summarizations. And this is where I got the pictures for the embeddings, right? So like these are all the things that I use to kind of like actually build this talk. And here's the last example of kind of like the images that I made from this, because I had written this back in June, right? So it's like you don't really know when the information that you're going to be used is going to be recontextualized by your brain in a different context, because again, that's what the brain wants to be doing with information. It wants to make it useful for threats and opportunities, and then it wants to forget things that aren't relevant. But computers want to basically do the opposite. They want to get through data sets really fast, but they want to store things really simply. So there's actually a video here where you can kind of like watch. I'll pause it real quick so you can just see. So you can see up top here, I'm like running this command here, which is basically taking this text that I highlighted. It's a time lapse, so it goes really quickly. And then it's loading in all those results. So it's kind of like a Google Doc where every time I highlight some text and I say like, go find all the entries that I've ever saved that are similar to this. And then basically the process is just me removing and kind of editing, using my human brain, the things that I think are actually important or relevant to the talk from the search results. So basically it's kind of like still using my own kind of creative choicing. And if you've ever read Bob Dodo's book about Zettelkasten and A New Way of Writing, it's kind of a similar concept where you build up this abundance of notes that you've taken in the past, and then you kind of like use that to narrow it down to a particular kind of talk or thing that you're thinking. And you can see me thinking with my computer basically, and these are all links to the things that I actually saved when I saved them. So here, let me move on. So let's kind of wrap this up with a summary and conclusion, and then we can just go to some questions really quickly. So brains aren't computers, right? They're two different things, and they're both good at different things. Brains are really good at embodied understanding of environments and cultures because they can contextually store things, but that's because brains need to survive, and they need to survive for the sake of the organism that they find themselves in. So they will, without qualm, lie to themselves when it's convenient in order to make the organism survive better, for lack of a better term. And they will just manipulate data in whatever way it sees fit. Computers, on the other hand, just really simply move through ones and zeros just insanely fast, like faster than a human would be able to comprehend, just billions of operations per second. But they both can interface with the world and process information. They just do it. Computers are like counters, whereas like brains kind of live in the environment that they find themselves in and kind of need to survive. So search and add are also inverse, right? So every time that you add something, you increase the cost of searching, and every time you increase the cost of adding, you decrease the cost of search. So we've been living in a world where we just kind of have trade-offs with these two things. It's like, how do I use computers to basically emulate all the ad cost for me so that I don't have to do it? But then when I search and add, it basically stays zero. So from that point, we get to strategies, right? Which are, again, these kind of techniques that we all study and practice, but they require buy-in and learning curves. So they treat symptoms, right? If you have a particular set of data that you're working on, which is just your email inbox, a strategy is good for your email inbox, but it's not good for information itself, right? Your email inbox isn't Twitter, it's not YouTube videos, it's not music, it's not all these other things that are also just information. It's just kind of like a strategy that works in a particular context. A data structure is almost the opposite. So a data structure is the lower kind of like information is information. It doesn't matter if it's like a song or a cryptographic code or like your bank account number. It's all just numbers, right? And in data structures only really care about the data itself, and strategies allow you to kind of make algorithms and judgments on top of it. So tags and headings are information taxonomy 1.0. They are extremely useful, especially because, like, again, humans have their own subjective individual understandings of information, but they're really brittle because basically you need to maintain a whole separate system every time you want to add a new piece of information. So you're like, here's a thing that I found the other day about Pokemon cards or woodworking or, Austin, Texas, and then you have to figure out where it goes. So you spend another hour figuring out where that Austin, Texas entry goes in your system. And by the time that you're done, you spent half of your day just doing that, right? Vector embeddings can help us by turning societal concept into numbers. And then we can rely on computers to find the closer numbers to each other to filter for us. So we basically are turning strategies of kind of understanding things as they are and turning them into data structures that computers can operate on. So creativity is about jumping through clusters of ideas quickly and reliably, right? So it's about, again, taking the idea of like, what does this thing remind me of, and what does that remind me of, and what does that remind me of? So by having a comment entry model, you can basically really quickly jump between old, maybe unrelated pieces of information because of the way that you're looking for them through vector search. So communication between people is a good example of this because this is a contract of conjectures. I'm basically making a claim, I'm making an argument, I'm using my words to get that argument across, and then your brain is deciding which parts are fair and which parts aren't through your own background and understanding of the world. So we can create this kind of experience, like I said, with our entry comment model. I don't remember the order of things, so sometimes I say something and then it comes in at the very next one. But yeah, whatever. By keeping the cost of search and add low, zero, that means that we can add strategies that allow us to make interesting outcomes from entries and comments from the past. And that was what you saw in the Google Doc and the video time lapse of me kind of actually making this presentation. So I think the real thing to wrap this up here is that, creativity doesn't happen in a vacuum, and neither does searching or adding. We have to deal with reality. We have to understand that the human brain works in a certain way. We have to understand that computers are built to operate in a certain way, and that information wants to do what information wants to do. And the more you fight information, the more you end up in a situation where you're just screwing yourself in the long term. So it's like, if you want to keep the cost of your system really low, and again, I don't mean dollar cost necessarily, I mean cost of actually being able to use it reliably without feeling stressed by it, you have to realize that I need to choose a structure that's as low level as possible so that I can maybe achieve this for the longest period of time as possible, which if it survives, if the cost stays lower than your lifetime cost, then that's like a big win because you would die before it finishes anyway. So it's like, who cares, right? So that's pretty much it. Any questions? There's a QR code here to the slides and the doc and everything like that that I use to the Google Doc that has the stuff that I use to make this talk. So yeah.